Good morning, ladies and gentlemen. What we're going to talk about today are some more theorems that deal with limits. Um, a couple different things here. The first one is a theorem that allows us to calculate some pretty ugly looking limits. It's called the squeeze, also known as the sandwich theorem. Okay, so in order to use the squeeze or sandwich theorem, the concept is that we know something about two functions and we know a little bit about a third function, and the question is about that third function. That may seem a little bit kind of like, what are you talking about? Before I get into the words here or all the math symbols, let me start off by drawing you guys a little picture. Let's say I've got some function f, and f is just this guy right here. I'm sorry, let's call that h, not f, for the reasons that are fitting my notes. Let's say I've got another function. I'm just going to change colors to kind of draw it. Let's go green. And my other function is f. And so here it is, my other function, just doing that, is f. Now the third function, the one I want to know about, is g. Now in my world, theoretically here, I know a whole bunch of stuff about f and h. I might know everything about them. I might know a little bit about them. But I do know definitely one thing for sure, that at some value here, which I will call a, that their limits are the same. As you go from the left and the right of h, you're getting to the same spot from the left and right of f. Now let's talk about that third function, g. I don't know too much about g, but I do know he is always in between f and h. And that's what this first statement says, that g is always in between f and h. So if I'm always in between, maybe I'm like this, or maybe I'm doing something like this, maybe I'm doing something like this, but I have to be in between here. Now I'm going on. Going on. That's G. What up, G? Now you notice F and H, they're kind of like, pieces of bread. And G is your bologna. So you're making yourself a bologna sandwich here. Hence the name sandwich, or sometimes squeeze theorem. I prefer squeeze theorem myself because the H and the F squeeze together at this particular spot so that G, who always has to be in between F and H, have the same limit. Again, we don't know much about G other than he's always in between F and H. But if the limit for f and h at a particular x value, which I called a, are the same, then f and h have to squeeze together around g and give it the same limit as well. That's the idea. Now, let me show you the practice. Here's my function that I want to find about. Think of that as like my g. Right? That guy right there, that's g. I don't know much about him. So let's break him down to his smaller part. The smaller part of him, the way I see it, is sine of x. Now, if sine of x is the smaller part, start to think about, how is sine of x bounded? Well, if you remember your trig graph, sine of x is always between -1 and 1. You know, it's always between -1 and 1. So that's the foundation, the building block, if you will. Once you have that, start to try to create the g function. G is the guy in the middle. So you say to yourself, what's missing? This guy's missing x squared. All right, fine, let's put him there. But in order to put x squared there, I also have to multiply the other parts by x squared. So my function is always in between -x squared and positive x squared. This is like my f and h from the previous. And here's my g squeezed in the middle. Now, I don't know much about this guy, but I do know a heck of a lot about these guys. And I can find the limits of those two. And that's what I'm going to look to do right now. So I'm going to take the limit as x approaches 0 of -x squared. And when you plug in the 0 into that, you get -0 squared, also known as 0. Now you're going to plug in onto the other side. Okay, 0 squared is still 0. Since these two numbers are the same, then that tells you that the limit of that guy has to be the same thing because he's squeezed in between the other two. So then the answer to this has to be the same 0. Another little example, we'll see how this guy works. He's different because it's cosine, and not just cosine, but cosine squared. So you're going to start off again by taking the smallest part of that, which is just basic cosine. And yes, it's the trig function for anybody that's wondering. Is it always the trig word? Yes, it's always the trig word. And cosine is between -1 and 1. Now let's make it cosine squared. Well, if I'm going to make it cosine squared, if you know anything about cosine squared, his values are always between 0 and -1. See, if I square the values, sure, all of these negative values, when you square them, become positive. That makes 0 to be the smallest value. Here's your cosine graph. Wow, right? So there's -1 and here's +1. So when you square all these y values, you have something that looks like this. Bump, bump, going like that. All right, so that the 0 will be the smallest value. But I digress. Now we're going to try to build it, so we're going to need to multiply it by x squared. And the nice thing is we're going to kind of be done here with the building part of this. 0 times x squared is 0. Okay, now that we've built the function in the middle, we are gonna go ahead and take the limits of everything. So take the limit as x approaches 0 of the number 0, which is just 0. Then we're going to take the limit as x approaches 0 of x squared, which is also 0. Now, since these guys are the same, by the squeeze theorem, the limit as x approaches 0 of the original question is going to equal the same value, which was 0 in this case. So that's how we use the squeeze theorem to find other limits. You're going to have 3 questions tonight to practice just that. Now, the next thing I'm going to show you, it does go along with theorems. There aren't going to be questions to practice on them, but I need to discuss them now because they fit nicely in the limit and continuity chapter. So you're going to want to go ahead and copy down and make the drawings that I'm about to show you. All right. So the next theorem is called the intermediate value theorem. And it says if f is continuous on an interval from a to b, and C is any number between f of A and f of B, then now this whole stuff says there exists an x value in the interval from A to B such that f of x equals C. So the upside down or backwards E, however you want to, that means there exists a value of x in the interval from A to B. ST is such that, that's how lazy us math people are. We come up for an abbreviation for 2 4-letter words, such that f of x equals C. So what does that mean here? All right, so here we go. We've got a very nice function. He's continuous, and that's the key thing. Oh man, stuff moving on. Continuous. That's the key part of this. From A to B, there's my x value. He's continuous the whole time. I didn't have to lift my pen in order to draw him. There he is. If I choose any number between f of A and f of B, before you question where that comes from, if this is the A value, that's the f of A value. If this is the B value, that's the f of B value. So now if I pick any number in between the f of A and f of B, I'm going to call it C, that C's on the graph, and the x value that spits out C has to be between A and B. It can't be outside the interval. So we're going to come back and talk about the intermediate value theorem and his relevance, but I'm just fits in nicely with the whole continuous part of this chapter. Continuity is a pretty important thing. Now there's a corollary to the intermediate value theorem, which means follow-up. And it basically says this: if f is continuous on A to B, and here's where things are different, f of A and f of B have different signs, one's positive, one's negative, then there exists an x value in the interval of f of A and B such that f of x equals 0. You're like, what are you saying there, dude? Check this out. If f of A is negative, f of B is positive, then there exists an x value somewhere where he's got to cross the x-axis. The importance of the corollary is it discusses that continuous functions have roots as long as you have values on either side. It has to cross the x-axis at some point. Okay. The main homework tonight, there's 3 questions that deal with squeeze theorem. Hopefully you can check